everyone, today we are going to learn how to find the inverse of a logarithmic function as well as an exponential function. And then on top of that, we are going to learn how to graph logarithmic functions as well. Before we get started, I would like you to please evaluate the following logarithms. We have log base 16 of 4, log of 1,000, log base 4 of 8, log base 1/2 of 1/16, and the natural log of e to the 8th power. I strongly recommend that you use these strategies that I taught you in the last lesson to help you evaluate each of these expressions. Problems like these will certainly be on your mini quiz that's coming up later on. So please pause the video, try these problems on your own without a calculator, and when you have an answer, then we're going to go ahead. I want you to restart the video and I'm going to go ahead and show you what the answers are, and we'll see how well you did. So I already did it for you in number 1. I let the expression equal x. So what I'm going to do is I'm going to let all of the other expressions equal x as well. So when you have it equal x, that helps us to change the expression into exponential form. So this is going to be 16 to some power is equal to 4. I recommend strongly that you change both of the bases to be the same number. And I know that 16 is really 4 squared, so that's 4 to the 2x is equal to 4 to the 1st. So when you have the same base, we set the exponents equal to each other. So 2x is equal to 1, dividing both sides by 2, x is equal to 1/2. And that is your answer, x equals 1/2. Next, whenever you see a log alone, that means the base is 10. So this is 10 to what power is equal to 1,000. So 1,000 is actually 10 to the 3rd power. So we have 10 to the x is equal to 10 to the 3rd. So that is x equals 3. Next, I have 4 to the x power is equal to 8. Well, I can't change 8 to have a base of 4 and vice versa. So what I would recommend that we do is we change 4 to have a base of 2, so to make that 2 to the 2 squared, or 2 to the 2x power is equal to 2 to the 3rd power. When they have the same base, we're going to set our exponents equal to each other. So we have 2x is equal to 3, dividing both sides by 2, x is equal to 3/2. For number 4, our base is 1/2, and I'm raising it to the x power is equal to 1/16. So what I'm going to do is I'm going to rewrite, I can work with the 1/2 or I can work with the 2. It's your choice. I'm probably going to work with the 2. So this is a 2 to the 1st power, so I'm going to make that 2 to the negative 1st power. So negative 1x is equal to, 16 is really 2 to the 4th, so 1/16 is 2 to the negative 4th power. So I'm going to set negative 1x is equal to negative 4. I'm going to divide both sides by negative 1, and I find that x is equal to 4. And finally, the natural log means that the base is e. So if I have e to the x is equal to e to the 8th, then that means that I have the same base, x is equal to 8. And this is something that is going to be a part of today's lesson. If you ever see ln of e together, the answer is going to be the exponent. So if you ever see this indicates the number 1. The natural log of e is the number 1. So it kind of like cancels out and leaves you with the answer, or leaves you with the exponent. And that kind of like leads into what our first topic is for today. So before we start talking about that first topic, let's look at our learning targets. I want you to be able to say, I can use inverses to simplify logarithmic expressions, and I can find the inverse of a logarithmic function and an exponential function. So we're going to be working with both logarithmic functions and exponential functions. They are inverses of each other. And we're going to talk about how to find those inverses in just a second. And then I want you to be able to say I can graph a logarithmic function or graph logarithmic functions using a parent function, reflection, stretch, shrink, translation table. So like I've been talking about a lot this past week, everything changes and becomes the opposite whenever we are graphing logarithmic functions. So just be prepared for that for today. So let's go ahead and talk about some inverse relationships. By definition of a logarithm, it follows that the logarithmic function of g of x is equal to log base b of x. It is the inverse of the exponential function f of x is equal to b to the x power. That means that g of f of x should equal x, and f of g of x equals x, because we know how inverses work. If you were to plug a function into another function, you know that they're inverses if f of g of x and g of f of x end up equaling x. Here's the how. So g of x is log base b of x, and we're going to plug in f of x into that function. So this is going to be g of b to the x power, since that's what f of x is. And I'm going to substitute that into my function. So I'm going to end up with log base b of, I'm going to substitute for x, b to the x power. Okay, now this is going to equal something. I already am using the letter x, so I'm going to call it a question mark. So if I were to rewrite this expression in exponential form, b would be my base, so I would have b to the question mark power, because question mark would be my exponent, is equal to b to the x. So what does the question mark equal? Well, the question mark would have to equal x. So that's the long way of approaching these problems. But the shortcut is, if you see log base b of b anywhere in a problem, log base b of the same number, these two numbers are the same, the answer is automatically your exponent. Because log base b of b would cancel out, it would equal the number 1, and your answer would be x. The how was just what I showed you. Rewriting the problem in exponential form, you see that the answer would simply be the exponent. Let's go ahead and look at the next part. We have f of g of x. So f of g of x is log base b of x. So I'm going to write log base b of x. So if I were to substitute log base b of x into b to the x power, I would have b to the log base b of x power. So this would equal, if I were to rewrite this expression in logarithmic form, I would have to have it equal something, so I'll call it question mark. So if I were to rewrite this in logarithmic form, it would be log base b of my answer, which my answer is question mark, is equal to my exponent. My exponent is log base b of x. Notice that both of these have a log base b. So that means what's in the x position? That's the question mark. So question mark would equal x. So long story short, if you see a base being raised to log base b of that same base, if you see log base b of b, log base b raised to the, b raised to the log base b, where you have these two bases being the exact same number, your answer is going to be the other value. It's going to be x. I know it sounds confusing, but I don't want you to think about it too awful much. Just look for this pattern. So like in example number 1, we have, I'm going to do it the long way and I'll do it the shortcut. If I can make this become clear, hopefully I can. All right, so in letter A, we have 10 to the log of 6.7. So we can rewrite this. I'm going to make this equal to a number. We'll call it x. That might be helpful. And if I were to rewrite this in logarithmic form, we'll have log, our base is 10, of our answer is x, is equal to our exponent. So that is log, you can write it as base 10 of 6.7. So we have x and 6.7 are in the same position, so x is equal to 6.7. And that is it, that's your answer. Or you can notice that the fact that we have a base and then log of the same base, that part cancels out and our answer is simply 6.7. For letter B, we can do the same thing. We can rewrite this using, I'll call it a question mark, or we can call it y, whatever it is that you want to do. I can write this as 2 to the question mark is equal to 16 to the x power. So I can rewrite 16 using a base of 2 and make this 2 to the question mark is equal to 2 to the 4x power. So what would x equal, or what would this expression equal? Well, question mark would be equal to 4x. So what's our question mark, or what's our answer going to be? Simply 4x. There would not be any solving for x in this case. We would be simplifying the expression. Using the shortcut, we would rewrite this as log base 2 of 2 to the 4x power. When you see log base 2 of 2, that part cancels out, leaving us with simply the exponent, and the exponent is 4x. And that is it. That's simplifying the expression. Using the shortcut for letter C, I have 10 to the log base 10. So whenever you see 10 to the log base 10, that part cancels out, so my answer is simply 7x. For letter D, 27, I know that that is really 3 to the 3rd power. So I have log base 3 of 3 to the 3x power. Log base 3 of 3, that part cancels out, and my answer is simply 3x. It's simply your exponent. It's what you have essentially left over. That's going to be your answer. All right, so now what we're going to do is we're going to identify or calculate the inverses of logarithmic and exponential models. So whenever you calculate an inverse, please note that a logarithm is the inverse of an exponential, and an exponential is the inverse of a logarithm. So they go back and forth. So whenever you're trying to calculate inverses, the first thing that we do, just like we did in chapter 6, is we're going to interchange x and y. We're going to switch their positions. Please remember to skip this step when using models. So models means that you're talking about problems that have context. If you have a problem that's in context, do not switch the x and y values. Simply solve for the other variable. So I'm writing, do not switch x and y, just solve for the other variable. All right, so the first thing we're going to do is we're going to switch x and y. Then we're going to rewrite using exponents or logarithms. So if you start with a logarithm, you're going to switch to an exponential. If you start with an exponential, you're going to switch to a logarithm. So logarithm will be switched to exponential, exponential will be switched to logarithm. Then we're going to solve for y, and then when we finally have our answer, we're going to rewrite using f inverse of x. Let's go ahead and look at letter A. Step 1. First of all, A, B, and C have no context with them, so we're immediately going to switch our x and y values. So x is equal to log base 3 halves of y. Next, I'm going to, because this is a logarithm, I'm going to rewrite it using exponential form. My base is 3 halves, my exponent is x, and it is equal to y. What's cool about that is y is already alone. Awesome. I have my inverse function. I'm going to replace y with f inverse of x. So 3 halves, I'm going to raise this whole thing to the x power, just so that it doesn't look like just 3 is being raised to the x power, is equal to f inverse of x. And that is our answer. There is nothing further for us to do. Letter B. This is technically starting in logarithmic form. So the first thing I'm going to do is I'm going to switch my x and y values. So I'm going to write x is equal to the natural log of y minus 4 into parentheses plus 5. And so now what I'm going to do is now I'm going to solve for y. So before I do that, I actually have to get the logarithm alone first. So that's what we're going to do first. We're going to get the logarithm or the natural log alone first so that we can rewrite it using exponential form. So I'm going to get the natural log alone first. So I'm going to start off by subtracting 5 on both sides, and when I do that, I have x minus 5 is equal to the natural log of y minus 4. Now that I have the natural log alone, I'm going to now rewrite in exponential form. Remember that whenever you see a natural log, the base is e. So if you need to rewrite this as x minus 5 is equal to log base e of y minus 4, that's not a problem. You're more than welcome to do that, especially if you're a visual learner. If you can already see that the base is e, then that will help you out tremendously. So what I'm going to do is I'm going to rewrite this as e raised to my full exponent of x minus 5 is equal to my of, which is y minus 4. At this step, we need to get y alone, so I'm going to add 4 to both sides. Please be careful with how you write this. E has an exponent, that's x minus 5, and then we're adding 4 to it. So you need to make sure that you make your exponent look little and what you're adding look like it's the same size as the letter E. So please be careful with how you write it. Now that y is alone, I'm going to rewrite that using inverse notation. And here's my answer, e to the x minus 5 power plus 4. And finally, letter C, I'm going to start off by switching my x and y values. So I have x is equal to 7 to the 2y power. This problem is starting off in exponential form, so I'm going to rewrite it in logarithmic form and make sure that my y is alone. So my logarithmic form is going to be log base 7 of what my answer is, so that's of x is equal to my exponent, which is 2y. Y needs to be alone, so what I'm going to do is divide both sides by 2, and so my answer is going to be log base 7 of x divided by 2 is equal to my inverse. So what we did here is we switched our x and y values. Then if it was in logarithmic form, we switched the form to exponential. If it was an exponential form, we switched it to logarithmic form. And that's how you calculate and find your inverses. Let's go ahead and flip the page. Now what we're going to do is we're going to actually graph logarithmic functions. So what's interesting about log base b of x and y equals b to the x power is that they are inverses of each other. They are inverse functions. So the graph of y equals log base b of x is shown below, and it's shown for both b is greater than 1, which means that it was an exponential growth function. So we're going to call that a growth function. Or for b is in between 0 and 1, which indicates that we have a decay function. So both are going to have, there's going to be somewhere b value is going to be of growth and somewhere it's going to be of decay. But do note that they are inverse functions of each other, so that means that the graph of y equals log base b of x is going to be the reflection of the graph of y equals b to the x in the line y equals x. So it's just going to be a reflection of what we have already been working with. So here are the graphs for both, and so here are some key information that you need to know. Please note that the y-axis is a vertical asymptote, which means that our vertical asymptote is going to be x equals our h value. So there's still going to be h's and k's. It's going to be x equals h of the graph y is equal to log base b of x. The domain is no longer going to be all real numbers. The domain is going to be, for our parent function, it's going to be x is greater than 0. But in general, it's going to be x is greater than h for our domain. And you have to decide what that h value is from the function. So our functions for logarithms is going to be y is equal to a times the log base b of x minus h plus k, the same exact form that we've always had. The difference is that there is no r in these types of problems, so we won't have to deal with any sort of reflection across the y-axis like we did before. So the h value is still going to be on the inside, your k value is still going to be on the outside, and we still will have a number that could potentially be in front. All of the other rules that we've ever had for a's, h's, and k's will still apply, but the difference is that your domain is now going to be restricted, and it's going to be based on h. X is greater than h. Your range now is going to be all real numbers because we're going to have an arrow technically pointing up and an arrow technically pointing down for both types of logarithmic graphs. The asymptote is going to be based on the domain. It's now going to be x is equal to h. So another thing that's going to change is your parent function. So what I think I want to do really quick is kind of show you the difference between exponential versus log before we actually get started with graphing. So here's exponential versus logarithm. So the first thing I want to talk about is the parent function. Because they're inverses of each other, the parent function used to be 0, 1, 1, comma, b. Now, because they're inverses, that means that the x and y values are going to change. So my parent function is going to go from 0, 1 to 1, 0. Instead of 1b, it's now going to be b, comma, 1. So my parent function ordered pairs are going to switch. The next thing is that the asymptote for exponential used to be y equals k. Now your asymptote is going to be x equals h. The asymptote used to be horizontal. Now the asymptote is going to be vertical. So everything is changing. The domain for exponential used to be all real numbers. Now the domain is going to be restricted, and it's going to be, it's going to be x is greater than h. We are not going to be exploring when x is less than h, so that's one of the nice things that you're going to see. It's always going to be x is greater than h. Your range for exponential was either y is greater than k or y is less than k, depending on if the graph had a reflection across the x-axis. Now for logarithmic functions, the range is going to be all real numbers. So that is how everything changes. So this is something that you're going to have to make sure that you study. So I would probably study this chart because there's going to be both types of functions that are on your test. All right, here we go. Let's go ahead and graph these. The first thing that we want to do for these types of problems is you want to identify if you're going to be dealing with a growth or decay, and it just depends on what your b value is. Once again, your b value is greater than, if your b value is greater than 1, you'll have growth. And if your b value is in between 0 and 1, we'll have decay. So it's important that you have an idea if your graph is going to be increasing or decreasing. Next, we're going to be working with the parent function ordered pairs, 0, 1, and 1, comma, b. Oh, sorry, excuse me. 1, 0, and b, comma, 1. Blah. So we're going to be switching those around, 1, 0, b, 1. Then we're going to create our table of values using our points and connect using a smooth curve. We're going to list our domain, range, and our asymptote as well. So the first thing I'm going to do for y equals log base 2 of x is I'm going to identify what my a, b, h, and k values are. In this case, there's an invisible number 1 in front of the logarithm, so a is equal to 1. My base is 2, so b is equal to 2. My h value is equal to 0, and my k value is equal to 0. Now I'm going to create my table. So I'm going to write parent function. My parent function is going to be 1, 0, and then b, which is 2, comma, 1. In this case, I do not have a reflection. I do not have a stretch because my a value is equal to 1, and my h's and k's are both equal to 0, so I'm not adding or subtracting anything. So my ordered pairs are going to be 1, 0, so I'm going to plot 1, 0, and 2, 1. I'm going to start here and go through my points. Now it's going to continue down, and it's not going to cross the axes, and that's because I actually have a vertical asymptote in this case. My domain is going to be restricted. It's going to be all values of x greater than 0. My range, I have an arrow pointing up technically and an arrow pointing down, so that means my range is going to be all real numbers, and my asymptote is going to be at x is equal to 0. So I actually have a vertical asymptote right here. So I need to make sure that I show that there's some space in between my vertical asymptote and my graph. Please do not make your graph cross the y-axis. Please do not do that. All right, so that was letter A. Here comes letter B. For letter B, we have y is equal to log base 1/3 of x. So my A value is equal to 1, my B value is equal to 1/3, my H value is equal to 0, and my K value is also equal to 0. I'm going to create my table, and my parent function in this case is going to be 1, 0, and my B value, which is 1/3, comma, 1. Because my B value is a number that's in between 0 and 1, that indicates I'm going to have decay. Whereas over here, technically from left to right, my graph is growing, so this is considered growth. Over here would be considered decay. And that's because our B value is greater than 1, and over here, my B value is in between 0 and 1. I do not have a reflection because my A value is not negative. I do not have a stretch because my A value is 1. And I don't have a translation, and that's because my H's and K values are not other numbers. We're not adding or subtracting anything. So this is going to be decay. So I also know that my domain is going to be all values of x greater than my H value, and my H value is 0. My range is going to be all real numbers, and my asymptote is going to be x is equal to 0, which is a vertical line. So I'm going to go to my asymptote, and I'm going to draw a vertical line, a vertical dashed line. Please do not make it solid. I'm going to plot 1, 0, and 1/3, so that's going to be further back. So 1/3 is actually further back. It's not going forward, so that's going to be a little bit different than what we're used to. 1/3, comma 1, so that's going to be up here, and that's just going to be an approximation. So going through those points in the order in which we graph them, I now am going to draw like this stretched out J graph, and this is what our graph looks like. There's nothing further for us to do. All right, we have 2 more graphs, and in these 2 graphs, we're actually going to have a transformation. So for letter C, we have log base 3 of x minus 1 plus 2. So in this case, my A value is equal to 1, my H value, or my B value, excuse me, is equal to 3. That indicates that I'm going to have a growth function because my B value is greater than 1. So my growth function is going to look similar to this function that we have right here. It's going to have a similar shape. My H value is the opposite of what I see inside. The opposite of a minus 1 is a positive 1. And my K value is exactly what I see, so it's equal to 2. So now I'm going to create my table. Here's my parent function. My parent function is going to be 1, 0, and then my B value, which is 3, comma 1. In this case, I do not have a reflection. I do not have a stretch, and that's because my A value is equal to 1. But I do have a translation. I'm going to take all of my x values, and I'm going to add 1, and then I'm going to take all of my y values, and I'm going to add 2. So 1 plus 1 is 2, 0 plus 2 is 2, 3 plus 1 is 4, and 1 plus 2 is 3. These are going to be the ordered pairs that I'm going to plot. Before I plot, though, I strongly recommend that you come up with your domain, range, and asymptote. My domain is going to be all values of x greater than my h value, which is 1. My range is going to be all real numbers, and my asymptote is going to be x equals my h value, which is 1. So I'm going to graph my asymptote first. And I'm going to plot 2, 2, and 4, 3. Going in order in which I plotted the points, I'm going to have my graph approach the asymptote but not cross it. And that is the graph. There's nothing further for us to do. Last problem, feel free to pause the video if you want to try this one on your own, but then make sure that you restart it just to see how well you did. So let's go ahead and look at letter D. For letter D, we have our A value is equal to 1. My B value is equal to 1/2. My H value is not the number -3. My K value is -3. Notice that -3 is not inside of any parentheses. So if you want to rewrite this as log base 1/2 of x minus 0 minus 3, that might be a good thing. Our H value is actually 0. Now I'm going to create a table of values. My parent function is going to be 1, 0, and my B value, which is 1/2, comma 1. The fact that it's 1/2 indicates that we are going to have a decay function, which means that the shape of my graph is going to be similar to what I had for letter B. It's going to be decay. Going from left to right, it's going to be decreasing. So I do not have a reflection in this case because my A value is not negative. I'm not going to have a stretch in this case because my A value is not a number other than the number 1. And I will have a translation. My X values will stay the same, and my Y values will be decreased by 3. So I'm going to have 1, -3, and 1/2, -2. These are going to be the ordered pairs that I'm going to plot, but before I plot them, I'm going to identify my domain, my range, and my asymptote. My domain is going to be based on my H value. It's going to be x is going to be greater than 0. My range is going to be all real numbers, and my asymptote is located at x equals h, which is 0. So x equals h, that is on the actual axes, and we still draw in the asymptote, even if it is on the axes. I'm going to plot 1, -3, and 1/2. So this is one of those ones where you have to kind of go back. So 1/2, -2. So that's going to be this ordered pair, and plot them in the order in which you graphed them. So I'm going to have my graph approaching the asymptote and then decreasing rather quickly and like flattening out. How flat it needs to be, I'll let that be up to you. Essentially, I'm going to be looking for, does it have a general curved shape? Does it cross the asymptote? Did you graph the asymptote correctly? Did you plot your points correctly? How big or wide it becomes, I'm not going to be too much of a stickler on that. But that is the end of this lesson. Hopefully, it's not nearly as bad as what you think. If you do have any questions over anything, especially identifying inverses or working with the special inverse relationships where they eliminate, please make sure that you let me know. Otherwise, I hope you have a wonderful day.